So just to start, any questions about where we are, where we're going? Really hunky-dory? Okay. Huh? Okay. All right. So last time, right at the end, I introduced the concept of the density of states. What I basically said is the probability of E between E and E plus dE. I keep having to write things like that, but there's just no way around it. And again, why am I writing something as complicated as that? Simply if we're not talking about discrete energies, but continuous energies. There's the probability of an energy, and that we've now found. That's that Boltzmann term, E, some constant, which I have to find by normalizing, times e to the minus energy over kT. But this is the way we're going to talk about the fact that at an energy, there may be more than one state. So this term here, I wrote this before, this is the number of states with E between E and E plus dE. Now, we're going to calculate that for a case. And also, this is something that you need to know. Okay, I think I've given you a homework problem where you calculate the density of states, and that's a good sort of homework/exam problem, is to calculate it in a couple of different cases. Okay, so you do need to be responsible for this. So let me just start out with a simple example. And sorry, and d of E, let me just, to define terms, d of E is called the density of states. Okay. So an example, this is in the book, the harmonic oscillator with the quantum version. Let me do the example, and then I'll give kind of a more general formula. And maybe the formula will make more sense if I do it this way, rather than give you the formula and then calculate the example. In the harmonic oscillator, the energy of a state n is this number n times h bar omega naught. Right? Actually, I dropped 1/2. Okay, but that's what I did, and the book does several times when we talk about the statistics of that system. Okay, so this is straightforward. Remember, in the harmonic oscillator, you could have an energy, n was 0, 1, 2, etc. It's just a quantum number. All right. But if I think of, especially if n is large, even though strictly speaking we're going to apply this for n being large or small. But think of n being large for a second. If n is a large number, if I told you n was 100, and I told you, oh, within the range of 100 to 105, so for dn being 5, some delta n being 5, how many states are there? Okay, then we would just say, so let's take n to be continuous. Then dE equals h bar omega naught dn. It's just a really simple idea. So if this were 5, well, sorry, and I would have this relation between dE and the 5. Rewriting this, dn dE is 1 over h bar omega naught. I said it backwards. I wouldn't ask between E being 100 and 105. I said that backwards. if I told you the energy was some value such that n was up near 100, and I told you I had a range of dE, then how many states would there be? There would clearly be dN would be 1 over h bar omega naught dE. Okay? That would be the number of states in some energy range E. And therefore, dN dE is 1 over h bar omega naught. Now look at the definition I had over here. I said I wanted this thing, capital D times dE, to be the number of states in the energy range. I think you can see then that this has to be d of E. This is the number of states in the energy range, and it's equal to some coefficient times dE. All right? So this is actually the more general formula. So the general formula is if n is equal to somehow a number of states at an energy, then dN dE is equal to the density of states. It's really simple to write, and it's actually in many cases fairly straightforward, but sometimes a little bit subtle to actually calculate. And you have to find this for each different situation. Okay? And it is, maybe I played a little bit fast and loose here, although I hope it's okay. You know, n was just some number, it's this quantum number. But in fact, that is, you know, a number of states in a way, right? I mean, it is, just because, look, this is the energy, and then it has this form, and there's just this number here. And if I'm in some range of energy, dE, there will be some range of numbers, dN, and this will just be a relationship between them, right? It's sort of that straightforward, all right? So the trick in calculating the density of states is actually this bit. You have to somehow, and it's a little bit different in each problem, you have to somehow figure out a formula that relates some number of states that's associated with an energy. And sometimes it is a little bit funny in the sense that this didn't start out being a number of states. This just started out being a quantum number. But in fact, it represented that. It did work out that way in this case. Okay? So that's the density of states. And I'm going to work that out for a more interesting case in a while, probably Wednesday. Okay, any questions? All right, so let me stop there. So this is something you should know. It's the density of states. Now I have to do a little more talking. Okay, so I had this idea that the probability of an energy in some range is the probability of that energy times the number of states in that energy range. And that's good. But it turns out that's not always, in fact, that's usually not what I want to calculate with. So instead of probabilities, we want to talk in terms of sort of average numbers. By average numbers, I simply mean, instead of saying, what's the probability that you have, okay, so I have a system and I'm looking at some particles. What's the probability that some particle is at some energy? I instead want to, I want to ask a question which is going to rely on this Boltzmann probability, but it's just a little bit different. I'm going to ask how many particles have an energy. This is a bad sentence. You use average number of particles with an energy. That's what I wanted to say. So instead of the probability of an energy, that's what I want to say. Let's look at the average. Let's look at an average number of particles with an energy. Okay? So for instance, and so this statement here becomes so the number of particles with E between E and E plus dE is going to equal, I'm going to write N of E dE delta E, where this is the average number at E. All right? I know this feels a little bit ponderous, but I just have to make a shift. Okay? And for distinguishable particles, for distinguishable classical particles, okay, N is just the total number of particles times the Boltzmann term. Let's say, I'm even going to stick an S back on here, just to be very clear. So if I say how many particles are in a given energy, E sub S, some state S, this is the probability of the state, and then if I just multiply by the total number of particles, it's really very straightforward. In fact, this whole business here is just this with an N total stuck there. That's all it is, okay? But the reason I belabor this is because when we talk about quantum systems, this doesn't quite hold, okay? Things get a little weird because, and this was developed first. This was the 19th century development before anyone knew anything about quantum mechanics. And you just write this, and you probably wouldn't be, I probably wouldn't have written all this stuff about a probability and then switched over to talking about a number, the average number. But in quantum mechanics, this just gets a little bit weird because of a couple of things. One is this indistinguishability of the particles, right? I mean, that is a very weird property of a quantum mechanical system where I can't count the particles. Another reason is that the fermions and the bosons act very different. Okay, so then this is very practical. I mean, well, to the extent that quantum particles are practical. But this is really concrete, okay? Not a bunch of writing, okay? They're really different. If I have particles in a box, I have a bunch of them, and they're bosons, I mean, I've said this before, but I'll say it again. If they're bosons, I can just stick them all in there, and they can be in any state they want. And so, for instance, the lowest energy state is that they're all in the ground state, and they're all in the same state, right? But if they're fermions, and I start to put them in, if they don't have any, well, since they're fermions, we have to talk about spin. Suppose they're spin half, they're electrons. I can put two of them in the same energy state because one will be spin up and one will be spin down. And then the next ones have to go in the next energy state, etc. And so they're going to stack up to really, really high energies. And the book kind of punts on being rigorous at this point, and I'm going to sort of punt on being rigorous at this point. But the fact is you can't say something as simple as that in this case. And it just is more useful to talk about this, this average number of particles at energy E. Sometimes it's called the occupation number. It's just a more useful thing in a quantum system. And I've kind of hand-wavingly justified it, and then I'm not going to try anymore. But that's just what we use. We talk about this occupation number. Right? And the occupation number, I mean, in a quantum sense, it's a nice term. You're basically saying, I've got a particle, I've got a box, and I've got some average set of particles in there doing a statistical mechanical thing. What I want to ask then is, on average, how many particles are in the n equals 1 state? How many are in the n equals 127 state, et cetera? And so this occupation number, this n, now it's not this formula for them. This is only for the classical particles, this formula, is what I'm going to talk about. Okay. And then armed with this, which ultimately comes from a Boltzmann term, even when it's quantum mechanics, this exponential bit is going to still be there, although I'll show you in a second. It's a little different. Armed with this and that, I can go to town. I can calculate things. Okay? So just for completeness, to calculate the average value, and I'm going to follow the book's notation here, of some variable Q, which depends on energy. It might not depend on energy, but it might, because it could be energy independent, but let's assume it depends on energy. Otherwise, it's actually not going to have an interesting average. Q average, I'll want to write down the number of particles, let me back the integral out. I'll want to write down the number of particles, the occupation number, the average number of particles that have an energy E, times the density of states times dE, which is the number of particles in a range of energies around that energy. And then that's a probability. So I just multiply by Q, and also I may or may not, and I'll just always pretend I haven't yet, so I may or may not have formally normalized this yet. So assuming I haven't, then I write down the normalization, which was that the sum of all occupation numbers times the density of states times dE. I had to integrate that to find a normalization. All right? I mean, if you will, let me just erase something and I'll put it back up. Right? This actually comes back as a probability of energy E. Right? All I did is I multiplied by capital N, and I had to take the density of states into account. Okay? But it turns out it's not just multiplying by capital N, as I'll show you in a second, but that just sort of conceptually. Okay, so that is an average quantity. And this is really it. I mean, I'm getting to where I'm done with all this formalism. I mean, this is it. Now, if it's a continuous thing, and even if it's a quantum mechanical system, it can easily be a continuous thing. If I think about a very large number of quantum states, and they're a real system, an electron in the middle. The electrons that are in there are fundamentally doing quantum mechanical things. They're fermions. They all can't have the same state. I don't know if you know this. If you have a piece of metal, a penny, pick a penny out of your pocket. The electrons in there behave as if they have a quantum wavelength. It's not quite the size of the piece of metal, but it nearly is. I mean, each electron in there is a particle in a box, and the box is macroscopically big. Okay? And so they really do, there's almost like Avogadro's of number of electrons all in one kind of particle in one quantum box, if you will, in any piece of metal. And they really act that way. Okay? So that is a thing where it's quantum mechanical, but you want to use integrals because, the number of states is immense. If it's not a huge number of states, you may well be just doing this. Summing over states S and then normalizing as well. Okay? And again, this n is going to somehow have a Boltzmann-ish term that takes into the energy account, energy dependence into account. So that's basically it. So if I ask you to calculate some average thing, and we did this last time, and we got to this point last time for the Boltzmann distribution, for the classical particles, we effectively just calculated n times d densities of states. That's what we calculated last time. All right? That was the Boltzmann distribution. It was the number of classical gas atoms that have, or molecules that have a given velocity. We didn't do it in terms of an energy, we did it in terms of velocity, but it was the same basic idea, okay? I mean, one of the challenges I have in teaching you this section is the book does a lot, and it's kind of things seem like things are just coming at you fast and furious. So I was trying to draw this connection that we kind of have to do these definitions, but the concepts are really not that many. Just these various ways of slicing a probability and an averaging. Okay. All right. So let's, so like I said, this is only true for classical particles, and there's a slightly different formula for quantum particles for n. And it has to be figured out separately for, actually, there's more than one thing that you have to consider. Is it a fermion or a boson? Those are very different because, you know, fermions, you can't have more than one particle occupying the same state. There's another notion, which is, can you just create particles or not? Okay? And there's really only one example of where you can just create particles. That's photons. And we'll do that now. I can just create photons. If I have the desk has got a temperature, it can create photons that have an energy that have an energy that can be created just by the thermal average of the molecules. So we're going to look at this, and this is the blackbody radiation I talked about earlier in the class. So we're going to look at that now. The random jiggling of the atoms in the desk cannot create an electron out of nothing. You can't just like give birth to an electron. If you tried to, you would need energy mc squared for the electron. Plus which, at a fundamental level, you can't just create a particle. You can only create a particle and its antiparticle, because there's a conservation of total number of particles, which is a quantum effect that we haven't discussed, but turns out it's absolutely a rock solid rule or law of the universe. All right? So that's a different sort of thing. And then so this calculation of this depends on whether it's a fermion or it's a boson, and whether or not the particle can be just created out of nothing. Basically, it boils down to massless particles, of which we only really know one, which is the photon. Although gravitons also ought to be that way. And so then you get different rules for those than for not. And if it isn't massless, you get what's called the chemical potential. And that's really beyond what I want to try to talk about in this class. So let's just do, and I'm only going to do, this actually is not in the book, and you're not responsible for what I'm going to do now, but it's just a kind of a cool derivation, and I want to show it to you. Okay, so I want to talk about photons. So these are bosons, and they're massless. Okay? So let me first have a Boltzmann concept. What's the probability that, sorry, let me not write that quite yet. When I have a quantum system, the basic idea is that I'll have a bunch of energy levels. Okay? Now, I'll come to why I might have energy levels associated with some photons. Basically, I'm going to stick them in a box and kind of treat them like the states in a box. But the main point I want is simply that I have these energy levels, 1, 2, 3, 4, 5, dot, 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 dot. And the question I'm going to ask is how many photons are in each level? That's what I've been saying. All right? So what I'll ask is I'm going to ask the probability that state S, or energy level S, has n sub s photons. In other words, if s is 4, how many photons are in the 4 state? Okay? And this is like, there's some energy, I'm going to use this terminology for the moment. Little epsilon for energy. Right? So it should be a Boltzmann idea. This is just this Boltzmann distribution. The probability that there should be n photons in state s, which has an energy E sub s, should be e to the minus, well, it's not just E sub s, it's ns E sub s over kt. Because that's the total number energy associated with sticking n of them in that state, right? And then I got to normalize it. I'll divide by the same term, but summed over all possibilities. So I am starting with the Boltzmann idea. I am starting with this Boltzmann probability. But to calculate this average number, I got to do something that's just a little more thinking. I have to recognize that I have a set of states and that the real physical system, okay, and here I do refer back to the fact that I had massless bosons. If I have massless bosons, if this, just take my word for it that we want to think of them as discrete states. But then if I think of this table, it can just generate some photons. The movement of the atoms can just, little electromagnetic radiator in there, and it'll just radiate it and create a new photon, all right? And it's just a question of how many of which energy, all right? And so that's a very straightforward way of writing it. The n is a little bit new, but that's the total energy of that state when there's n photons in it. Now, what are the rules for this sum? The rules for this sum is that basically ns can take on any value. There might be 0, there might be 1, there might be 2, there might be 3. If this was fermions, it would be no way. It would be 0 or 1, and that's it. Or if I take into account a spin, I could have 2 in there, but that's it. All right? So, okay. And I'll just sum over all possibilities. I'll sum over, this is a sum over all values of n. Okay, so that's the first idea. That's the probability that I'll have n in a state. Okay, you are not responsible for this derivation I'm about to do, but I think it's really kind of cool. And I promised you at the beginning of class I would actually explain about blackbody radiation. And since blackbody radiation is fundamental to our understanding of global warming and greenhouse gases, let's just go through it, and let's go through it in first principles. Okay? Okay, so if that's the probability of n sub s, what's the average number of photons in n sub s, in that state sub s? This is indeed, and I'm sorry for the terminology changes, but this is indeed essentially that capital N. It's the average number, or it's the occupation number. It's going to be, it's the average number of particles in E sub s state. Okay? It's got to be just the probability of having n sub s in this state, for which I have to, this is the Boltzmann term with the normalization written explicitly. But if I'm averaging a thing like a number, I write the number down and I sum over possibilities. Right? That's what I do. That's exactly analogous to this. Here, it's basically my function is q in a way. Although I'm not quite at doing q, I'm still just figuring out what the n thing is, the number is. So that's what it is. So that's straightforward. And now I'm going to do 3 bits of trickery. Really, really wicked trickery. Okay? All right. First bit of trickery. Oh, sorry. Before I do it, let me just to completely belabor it. I mean, writing this because the probability is that, this is nothing other than saying, right? That's all I'm doing. That is that. That's all I'm doing. Taking the average of something by knowing its probability, taking the thing, summing. All right. Okay, so what's the trickery I want to do? I'm going to this is just a shorthand because I'm going to get tired of writing it otherwise. I'm going to let y equals this sum. Okay? I'm going to this is just a shorthand, let x equals e to the minus es over kt. You know, the Boltzmann bit without the n. So this sum is just, this denominator, okay? So then y is the sum on ns x to the ns. And ns is running from 0 to 1. This is 1 plus x squared plus x cubed, right? And you know what this is, right? This is equal to 1 over 1 minus x. Everyone know that? Did people know where you can get that? You could do a Taylor expansion, or you can use this sort of argument, which is not very mathematically rigorous, right? But if you have the sum on x to the n, let's just suppose that's true. Then let's multiply both sides by 1 minus x. And this is the sum on x to the n minus x times x to the n equals 1. So this is 1 plus x squared plus dot, 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 minus x squared minus x cubed dot, 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 dot equals 1. And that cancels, dot, 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 and I have 1 equals 1. So it works. Better yet is to do a Taylor expansion on that, and then you'll just see. That makes me a lot happier. Anyway, fine. So that's y. All right? So that's the first thing, that this ugly thing in the denominator, and it's only true for this massless bosons where I just get to sum on all possible number that could be in there. I could have 1 million photons in there. This whole denominator is very simply written as 1 over 1 minus x, which is going to be 1 over 1 minus exponent of this thing, right? All right, that's good. Now, what was the second bit of trickery? Yes. What is that? That looks like, how am I going to evaluate that? Because I found this trick to do the thing without the ns, but here I have the ns. And what you realize is this is d by d es and I better multiply by minus kt. All right? So if I take the derivative with respect to energy, whatever that means physically, I don't care. I'm just being mathematical. If I take the derivative with respect to energy, n comes down, right? So can you see that that's all that is? And then the kt, I better write a minus kt there. All right? So this is equal to minus kt d by des of y, which is 1 over 1 minus x. And the last little bit, let's go right here. So if that's true, then the third little bit is not really so tricky, but so the denominator is y, and the numerator is minus kt d by des y divided by y. If I have the derivative of something with the derivative of something divided by the thing, that is equal to the same as the derivative of the logarithm of the thing. Okay? Because, right, you know, d log x is dx over x. So d by de of y divided by y is the same as this, right? Because if I start to take the derivative, I'll get dy des divided by y. It's only that. And, all right. Okay. I didn't really have to do this because I'm just now well, so let's take this derivative. So the derivative of the log of this, for some reason I'm having a brain seizure. Okay, yeah, I just wanted to do this. D by de sub s of the natural log of 1 over 1 minus e to the minus es over kt. All right. The derivative of, the logarithm of 1 over x is the logarithm of this, if you will, to the negative 1, which is kt d by des of the log of flipping the numerator up, flipping the denominator up. And a negative sign comes out front. Okay? So n sub s is, I'll just take the derivative of this and then I'll divide by it. So it's kt, the derivative of this with respect to es. The 1 goes away, I have a minus sign and a minus sign. 1 over kt, e to the minus, and then I divide by it. Okay? The kt cancels. And I just have this exponent over 1 minus this exponent. If I divide through by the exponent term, top and bottom, I get 1 over here, I get the exponent with a positive sign. And then this is that divided by that is 1. Let me write that cleaner, because this is an important result. I did a lot of work to get that formula. Okay? This is the average occupation number for photons. Strictly, it's the derivation. All it relied on is that I got to sum n from 0 to infinity. And secondly, I did not introduce a complication which talked about an energy cost of creating a photon other than just the fact that there's just a KT that does it. And I'll refer you to the book, the appendix. Actually, I lied a little bit. The book does have a derivation of the Boltzmann distribution. The old edition didn't. I was looking at that the other day. And it includes, if you do have a massive particle, but okay. You can look at that. But so this was not completely general. This was restricted to the case of photons. But there it is. And notice it's close to the Boltzmann distribution. The Boltzmann for the classical result was that n was just n total, a constant e to the minus energy over kT. If the energy is much larger than kT, this piece is bigger than 1. It dominates, this goes away, and this is 1 over it, and it is just that, although I've lost the n tot thing, okay? But there, it's always the case that there's a classical limit where quantum distributions start to look classical. And so just simply recovering this simple exponent of energy over kT is done. But at low energies, that's not the case, and it's this 1 over the thing minus 1 business, and it's just different. Okay? Now the book lists, there's basically several, there's the fermion case, there's the boson case. And then if you include that the particles that aren't massless, which is everything but a photon, there's another prefactor in here, which the book calls B, which is related to the chemical potential. And the book just lists those. I derived this one now for you, okay? Also, just because I think this sort of mathematical trick is cool. Maybe it's just me. All right? So that's the average number of photons that have a given energy. And at high energies, it acts like a classical result. And that's called the occupation number. Okay. Any comments or questions? Okay, so now though, all right, to get anywhere, I needed this number, and now I need the density of states, and then I'm home free. So now the density of states for photons is a little bit funny. Basically, okay, so I need the density of states. And I'm going to do the derivation of this. And a classic homework / exam problem is, if I do this in 3 dimensions, you do it in 2 dimensions. Or vice versa, okay? And it's straightforward. You'll see it's straightforward to go from one to the other. I'm almost out of time, and I'm covered in chalk. Let me just state the first idea that we need to do this, and I won't do any calculations. There's a funny business we do here, which in fact, I mean, I first saw it 20 years ago, 22 years ago. It's kind of sad. It still bothers me. But here's what it is. We basically pretend, I mean, there's ways of stating this. The way I'll state it is that we pretend that the photons are in a particle, or the photons are in a box. We put the photons in a box. With particle in box boundary conditions. Okay? That is to say, I'll make the photon fit in one wavelength exactly. That's a half wavelength. Or a whole wavelength, etc. That is to say, I'm going to make m lambda over 2s, so half waves, some number of them, equal L, where that's some box size. I'll do it in x. I'll do it in, this is an m sub x. I'll do it in y. And I'll do it in z. Now what's going to be funny is, I told you I wanted to talk about, actually I'm going to derive the temperature of the Earth based on what we're doing here, okay? And it's going to involve photons coming off the sun, which do that, and some other things, this density of states, and then the Earth radiating photons back out. And that's the calculation, the heat absorbed from the sun, heat radiated by the Earth. Where's the box? It's a good question. There is no box. Sort of like there is no spoon. But it turns out that this little bit of trickery, the other trickery I did was just math. This is a little more profound. The correct quantum mechanical treatment of these systems is to basically say that the photons obey a boundary condition on some length scale L, as if it's in a box and has to vanish. And basically what this is going to allow us to do is define energy states for it, right? Because if I do this, if I quantize the wavelength, remember, the energy is equal to Pc, which is h bar kc, which is h over lambda c, okay? So if I'm saying that the wavelength has these quantized states, I've said the energies have these quantized states, and I've sort of given meaning to this calculation by sort of arbitrarily introducing this box that the photons are in. But then what I'm going to do is I'm going to make the box really, really large, so these states are really, really close together. I'm going to go over to the continuum limit, and then the three box lengths, Lx times Ly times Lz, I'm just going to turn into a volume, and then I'm going to divide the volume out, and it's just going to be a normalization. And the box is just going to go away. The spoon will just go away. But this is going to allow me to calculate the density of states, and I get the right answer. And this is how it works, okay? So we'll do the mechanics of the calculation based on this kind of setup next time.